All right, hello everybody. Thank you for attending this session. My name is David Yu. With me here are Shiraz Sohail and Rob Fletcher. We are from the GeoAI team here at Esri. What we'd like to think of ourselves as the intersection between GIS and artificial intelligence. And today we're going to talk about driving intelligence from video and oriented imagery at scale using AI in ArcGIS. So in Esri, we tend to look at the world from one angle, top down, also known as nadir. And that view of the world has been tremendously helpful to us for various types of AI-driven geospatial analysis. Think of building footprint detection or swimming pool detection. But in many cases, just looking at the world with nadir does not equip us with enough information to be able to come up with useful insights. So consider road asset detection, damage reporting for insurance, or blight and graffiti detection, not to mention the sheer volume of high-resolution data that are out there from cell phone cameras alone. So it's important that we explore how AI can be leveraged to enhance workflows relying on obliques instead of nadir. And today, between Shiraz and myself, we'll cover a couple of these examples, and Rob will dive into real-time video analytics with Nvidia DeepStream. So I'm going to start off by talking about road feature detection and geotagging. This is a need we're starting to see a lot from government entities such as departments of transportation or public works, as well as companies with access to large amounts of mobile mapping system data. Many of these users are interested in driving intelligence from raw images or video inputs automatically and at scale. So mobile mapping systems, or MMS, for those of you who are unfamiliar with the term, are car-mounted GPS-enabled cameras that are capable of capturing large amounts of imagery at speed and at scale. These images typically come with a bunch of metadata such as vehicle bearing, car pitch, yaw, roll, latitude, longitude per frame, as well as the errors associated with each of these measurements. So these are the types of inputs we get to play with. But before I get into the project specifics, let me quickly go over what the road features, or some people call them road furniture, what these really are. So these are essentially assets that are placed alongside roadways or curbs that might be of interest to a large-scale collection effort. And the assets themselves can be various types of signs, guardrails, potholes, or even road cracks. Basically anything that can be visually identified from MMS imagery that can really typically be used to train a machine learning algorithm. The caveat is you need to have enough training data. And the business case for bringing asset detection to automation through machine learning is actually very straightforward. With DOTs as an example, in order to create and maintain a current asset management geodatabase, they typically would have to send work crews out to manually survey an entire road network, which, as you know, is both costly and also time-consuming. So sometimes, when a road network is fully surveyed, it's actually gone out of date. So to try and cut down costs, sometimes if the DOT has access to mobile mapping system data, they would hire analysts whose full-time job would be to sit down and comb through tens or even hundreds of thousands of images to see where they can identify some features and roughly estimate where these assets are on a map. And the only supporting data they get to work with are the latitude, longitude information associated with every image. Another business case that I think really drives home the need for automation is asset status or damage monitoring. If we're interested in preemptively identifying broken signals, damaged bus stops, or even sign drift, or to give early warning on newly formed road cracks, we really want to be collecting these MMS images a lot more frequently. And GIS is very good at identifying change detection to features on a map. So for instance, performing a spatial drawing between two feature layers of two different time steps would allow you to quickly filter out the 99% of your assets which remain unchanged and focus in on that 1% to really understand why that asset is no longer being picked up. So for this project, we collaborated with the Arizona Department of Transportation, who are interested in not only detecting street signs, but also classifying them into sign types and accurately geotagging each road sign so they can be placed on a map. And so here are a list of outputs we've been able to generate by having a trained model ingest raw MMS imagery. We've been able to produce minimal bounding boxes around these road signs and also classify them into different sign types such as exit signs, speed limit signs, or even the MUTCD compliant classifications. We can also pass these signs into an optical character recognition API to retrieve the texts that are written on each sign and also save that onto a geodatabase. We've also managed to infer where each sign is in a map by understanding how far each sign is away from the camera, since the latitude and longitude metadata that are paired to the camera, it does not reveal that information. And finally, we're able to persist these detections into a feature layer, which of course means that you can carry on with post-processing and analysis in ArcGIS Pro or ArcGIS Online. So I talked about inferring the latitude-longitude coordinates. This is important. This is an important output from the model because your object might be quite a ways away from the location of your camera. So oftentimes, just transferring that latitude-longitude pair onto your image, from your image onto your assets, is not going to generate feature points that are accurate enough. So there's a couple of ways to derive latitude and longitude pairs. The first rule of latitude-longitude inference is to always start from photogrammetry, especially if your frame rate is high enough that a single asset is captured multiple times along route. So leveraging photogrammetry techniques such as epipolar geometry would allow you to understand the placement of these objects into map space, which is going to be your safest bet because using photogrammetry is really going to give you the most accurate geotags. Short of that, if you have access to the focal length of your camera, the size of the CCD or CMOS sensor, and the object of interest is of a standard size, let's say if you know what the traffic signals are in real life, how big are our specific class of road signs or fire hydrants, you can use similar triangles to get a pretty decent estimate of the distance of the object to the camera. Alternatively, for this project, we're actually using a neural network approach to be able to infer the distance of assets from the camera for single images. So what you see on the left is the input image into the network, and the output shows a depth map of what the network thinks is the various distances of pixels away from the camera. So this is a network called monodepth, and like any other deep learning neural networks, there's a positive correlation between the number of training images you have and the accuracy of that output. So here it is again in the video format. So on the left hand side is the images that are being ingested into that neural network. And of course, you see these signs also have the bounding boxes associated with each of these image frames. And on the right hand side, we see the associated depth map for each image frame. So one of the problems of not using photogrammetry is the problem of having multiple detections. In other words, if you throw whatever detections you have on a map right now, you will likely see multiple points clustered together when these points really come from the same object. And this comes from the fact that you're always going to get an error from your distance measurements for every image. So these points don't really neatly stack together. And to get around this problem, we use clustering analysis tools such as the spatially constrained multivariate clustering tool within Pro. What this allows you to do is combine multiple feature points together based on their spatial proximity. And as an added precaution, if we have points that also exhibit the same sign class, we assign a higher probability that they should be clustered together. Then we simply find the cluster centroids and put them on a map. Now let me quickly show you what all of that looks like in an end information product. So what I have here is a operations dashboard. And as you see, I can filter these detections by different types of sign classes. I can also click on one of these points and have it display exactly what is the image associated with that point, what is the bounding box around it, and also what is the vehicle latitude and longitude, as well as the sign latitude and longitude. One of the really cool things that you see here is if I filter by mile markers, you see that indeed all of these detections are about a mile apart, which is a pretty good sanity check. Another thing that we can do is also filter these detections by signs that have detected text. So for instance, if I click on one of these detections here, you see the text really being picked up from the OCR pipeline. So for instance, you see, right here, because the sign is almost occluded, you see only half the text being picked up. Whereas for this sign, you see almost all of the text being picked up. So that's pretty impressive. So far, we talked about automated asset detection, and asset status or damage monitoring really falls under that same workflow. But what if there's a need for new asset installations or maintenance? Is there a way to update these assets in a geodatabase in real time from out in the field? Well, it turns out that is fairly easy to implement, and as part of the collaboration with Arizona DOT, we were able to use ArcGIS Collector to validate and update detected features within that same geodatabase in real time. We can also monitor these updates in the dashboard and have them show up in real time as well. A common question that we get asked a lot is how many sets of training data and labels do we really need? So unfortunately, there really isn't a standard answer to that question because a lot of it depends on the model you use, the resolution of your image, and the difficulty of the problem space you're trying to tackle. So however, it's always better to have an abundance of training samples rather than realizing at the last minute that you don't have enough. Fortunately, it has become quite standard now to apply image augmentation techniques to your training data. These are essentially random affine transformations applied to your input images and labels that will synthetically boost the number of training data you have by an arbitrary factor. So what you see here is the original input image on the top left, and then we see random dropouts as well as random rotations. Also, what you see here is the chromatic shifts for the different channels and so on. And if you're interested in applying these image augmentation techniques, it's actually built into the prepared data function of the ArcGIS API for Python, specifically in the Learn module. So the Python API documentation is a good place to start looking for these types of capabilities. All of our detection outputs for road signs are also MUTCD compliant, which means they are classified into 171 classes of signs. And here are some examples of these varying types of classes. So we have the detections in the image here, and also on the right-hand side we have what is the ground truth of that particular code, and what does that really look like. And so one of the interesting things you'll see is that despite the fact that some of these signs are fairly far away from the camera, we still have some very good detections of these road signs. And it doesn't matter how many signs there are per image, we can detect all of these signs and have them correctly classified. So of course, road signs are a very narrow type of road furniture. We've done very similar work for other types of assets. And the point I'm trying to get across is that the number of unique objects that can be detected is really infinite. So for instance, we've been able to do the same thing with road cracks. So as many of you may know, there's different types of road cracks. You have alligator cracks, you have transverse cracks, or longitudinal cracks. And the idea is because each type of road crack can be caused by a multitude of factors, and they also reveal differing insights, it's important to be able to classify them. And so this is what we've done here. We've been able to ingest video data from dashcam video feeds and also output bounding boxes around these road cracks and also classify them. And of course, in the end, we're putting everything on a map. We've also done some very similar work for water meters for city governments, where this is actually a segmentation workflow. So instead of bounding boxes, what you see here is the model was able to assign unique class values to every single pixel. So let's say if there's a positive detection for a water meter, then maybe the pixels associated with that water meter would get assigned the value of 1, whereas the background would be assigned the value of 0. So the top images that you see on this row here are the input images into the machine learning model. The ones in the middle are the ground truth values, or the ground truth labels. And these actual detections are being outputted right here. So it's actually fairly impressive too, because you see that each water meter is actually very, very small within that image. And it's quite impressive how the model is able to isolate that specific region as a water meter. So in terms of the machine learning workflow, this is quite complicated, but let me try and break it down for you. Just ignore the part at the bottom. So this is associated with actually coming up with the geotags per image. But let's say you just have access to the raw labeled data and also the metadata, as well as the raw images. What you do first is you would perform some sort of image augmentation to synthetically boost the amount of images you have. Then these images and labels would get fed into the detection network. And of course, if you have pre-trained weights, right, for some of these networks, you can load them in and retrain that over your new data set. And in the output, your model is going to come up with some sort of bounding box that might not necessarily fall on top of the actual ground truth bounding box. So what happens then is that some kind of error gradient is going to be calculated based on the difference in output between the ground truth and the output from the model. And that error gradient really gets back propagated into adjusting the weights from your machine learning model. So that's for just coming up with the bounding boxes. In terms of actually geotagging these road features, we're using, as I mentioned before, a network called monodepth, where you're feeding in that raw image into monodepth, along with some camera metadata information, right? So these are the vehicle bearing, the camera latitude, longitude, pitch yaw, etc. And of course, that is going to be able to give you the distance away, the distance of these objects away from the camera. And that's going to allow you to come up with these geotags. So what you saw on the previous slide really fits into this little red box here. So that's going to be your trained model. So for your overall project architecture or tech stack, what's going to happen is you have access to your raw MMS imagery. That's going to be fed into your machine learning model that's going to come up with all of these predictions and have them saved into a CSV file or what have you. At the same time, if you have access to some kind of OCR pipeline, so in this case we're using the Microsoft Computer Vision API for optical character recognition, we're piping that also into the output of the CSV file here. That's then being read into ArcGIS Pro, where we are doing the bunch of post-processing that I talked about earlier, which is namely using the clustering analysis to be able to understand where these points are really on a map. And of course, the output of that is the hosted feature layer that can be ingested into ArcGIS Online, that gets pushed out to the operations dashboard. And of course, simultaneously, you can have a different workflow that hits that same geodatabase in real time for new asset installations or asset maintenance. So now I'm going to hand it over to Shiraz to talk about feature extraction from Oriented Imagery.
Thank you, David. So what I'm going to be talking about is kind of a larger general version of object detection called segmentation, which David mentioned a little bit. And this is basically around taking every pixel of an image, for example, from a dash cam, and being able to associate a class with it. So I'm going to kind of reiterate some of the needs. I'll go over a possible methodology for doing this within a GP tool in Pro. I'll show some of the state-of-the-art results for segmentation, and I'll talk a little bit about actually tracking individual detections, which will lead into some of the additional parts with video analytics. So for the first part, just reiterating some of these needs, there's been more oriented imagery collected in the last decade than ever before, and this is really caused by not only multiple devices that make capturing that video very easy, but also the rise of industries that make heavy use of that type of video. So especially areas like autonomous vehicles, logistics companies, departments of transportation, and especially for those industries, there's a huge market in creating HD maps. So being able to understand, where a multitude of objects are, how they move, being able to get that information in either real time or something close to it. And the maps that are created as a result of that process are much more dynamic than the ones created from aerial imagery. They're usually much cheaper, and they contain a much richer description of assets, because there's more assets that are usually visible, especially roadside assets from this kind of video versus aerial. So firstly, what is the state of the art in this area? So what you're looking at is the output from several different models that are doing segmentation on dash cam footage. So this associated data set is called Cityscapes. It's a pretty popular benchmark. And the pretty popular metric for analyzing these kind of things is called MIOU, or mean intersection over union, which is, for example, if I predict an outline for a person in this image versus that person's true outline, what is the intersection of those two polygons, and what is the union that the connecting those two polygons forms? So that gives you a metric for understanding how good each of these individual object predictions are. But another thing you'll notice is that the video on the left seems to be running at almost real time. So that video is playing at about mid 20 frames per second, and that is around the upper bound for most of these state-of-the-art models for doing full image segmentation on high resolution video. So fairly close to real time, and there's about 32 classes that are being identified here. And this is kind of the historical progress, so you can see the huge strides we've made just from 2015. And each of those individual points are the name of the model that actually accomplished that performance. And that y-axis is the mean IOU that I mentioned. So my team was actually able to wrap this up into a GP tool to demo, but here's the general idea of what that GP tool contains. And this is something you can write today using some Python script and some of those models I mentioned. So the first part is really creating an input parameter for that image and an associated image pair or some kind of depth map. So David talked a little bit about depth maps and how those can be generated from networks or stereo. Another way you could generate them is if you have video, you can take pairs of successive frames. And the goal really in creating a depth map is, can you identify the position of one pixel in one frame and correspond that to the same pixel in another frame. And once you're able to generate a depth map, the tool would basically run one of those models I mentioned across the image and identify each pixel as one of the classes. So, in those models, there's usually 32 classes, which is a standard benchmark for cityscapes. And for each of those classes, you obviously get a spatial position. So what you can do, for example, in that G module, which is number 4 on that diagram, is take the centroid of each object. So for example, if you want to identify vehicles, you can see there's one vehicle in blue in that image. Take the centroid of that object and take the value of that pixel and look in the corresponding depth map to understand how far that object is. And if you have camera metrics, you can actually utilize that to get a lat long for that pixel on that object. And once you have that, you can easily write that out to a feature class, which, once you run this over a long enough video or a successive set of frames, you can get a pretty interactive and in-depth map of an area. And you can even use those points to, for example, populate 3D models in those areas. Now, before we step into Rob's portion, I want to just demo something we've been doing recently, which is actually identifying different types of driver behavior. So drone feeds are kind of an interesting medium in the sense that the geolocation portion is fairly easy. So you don't have things like occlusion here, you don't have things that contain different amounts of light refraction, or you don't have frames that are shaky or anything. You can pretty clearly identify if you have the extents of the drone feed and some camera metadata where each of these things are. And what we're doing here is we're not actually only just identifying those vehicles, we're using optical flow techniques that actually take each of those detections and persist it into future frames. And what this allows you to do is basically get a unique ID for each detection and to actually form a path. And this basically allows you to utilize a lot of path analysis methods to be able to understand what kinds of behaviors each of those objects is exhibiting. And so with that, I'm going to lead into Rob's portion. He's going to talk a little bit more about video analytics and how to do that at scale.
Thank you, Shiraz. Yeah, so we've been seeing a lot of demand recently for this type of video analytics. I'm going to go a little bit into kind of what people have been looking for and why they're actually looking for this. Real-time video analytics provides a lot of value to a lot of clients. Getting real-time information allows you to make much better decision-making because these things aren't aggregated over, large periods of time. For example, in the Department of Transportation space, a lot of times traffic counts and things like this are measured maybe on 1 or 2 days a year, and then that's extrapolated through the rest of the year to get estimates. You could obviously make much better decisions if you could know the exact count of cars right at that second. This also allows you to produce data that was just impossible to get a hold of before. For instance, the actual real-time count of cars going through intersections at any given moment across an entire city. But it's not also limited to cars. This could be any object you could detect in video. This could also potentially be shoppers at a store and trying to understand, where are shoppers going? What kind of products are they looking at more than others? Where are they spending their time in the store? And then coupled with AI, real-time data can generate much finer grained data than ever before. Maybe before there were ways to count, for instance, the number of people that walk into a store. But with AI, you can go a lot, like very far beyond that. You can see where did they go in the store, what were they looking at, where were they lingering, things like that. And in the Department of Transportation example, you can go from, maybe one of those strips that goes across the road, which just, counts the number of tires that bump over it, basically, into now we could count people and cars and trucks and bicycles and maybe even colors of cars, things like this. And so you're really transitioning from this realm of just counting things into being able to have much richer, more fine-grained data than ever before. Here's an example of using some video above some intersections to detect cars. And this is actually 12 cameras running object detection in real time, all simultaneously. So you see there's just the wealth of data that you can get out of this is really great. What a lot of departments of transportation are doing now is they have these video feeds up and they're getting all this data, but they just get piped into a room with, say 100 TVs, and one person just sits and looks at them. It's very difficult to actually capitalize on any of this information in that case. We've recently been working with Nvidia on a product that they have called DeepStream. This is a platform that allows you to do real-time streaming video analytics and deep learning. We've spent a lot of time with them coupling this platform with the Esri GIS platform. Here's a basic diagram of kind of the flow of data as it goes right now. You can collect this information from real-time cameras or from any sort of edge device, IoT sensors, things like that. They can be decoded or pre-processed in some way, for instance, maybe de-warping video or tiling or untiling video, things like that. They can then go into this track inference kind of module where this is where you can run deep learning models. You can run several deep learning models all in series to extract more fine-grained information each time. You can also run tracking on these things. So like Shiraz mentioned before, assigning a unique identification to each one of the vehicles that you see or any object that you detect in the screen so that you can track them all the way throughout and be able to get trajectories of these things. These can then be encoded in various ways. And also all of this data, the metadata from these is written out into a Kafka broker. So the Kafka is the real connection between the two platforms. We have several products that can read from Kafka brokers, such as GeoEvent or Analytics for IoT, can harvest all of this information coming in from there. From there, these things can be written into feature services that are updated live, and they can be monitored on dashboards or any other type of real-time monitoring that's provided in the platform. This also unlocks an entire world of analytics that you can do all in real time on all of this data. Not to mention that all of this data can be written for later consumption and later aggregated analytics as well. Just to give you a little bit of an example, here's a dashboard that we've created to visualize real-time counts of cars. This is a demo application that we've done where we've scaled this up to almost an entire city. It's not quite every camera in the city, but it's quite a few in there. And so you can see that in this dashboard we have all of these counts of vehicles actually coming in complete real time that are updating on this dashboard. So every vehicle that's driving through every one of these cones that you see on here, which is the cone of view of the camera, is being tracked and the trajectory logged in all of these so that you can go back and at a later time understand traffic patterns or even look for changes in patterns that you see currently here. For instance, maybe there was a road closure that you didn't know about caused by something you weren't aware of, and so you see a big spike in traffic in a part of the city that you don't normally see traffic at that time. This allows you to, in real time, dispatch maybe police officers or some other entities to go out and maybe direct traffic or find out why you're seeing a big spike in these things here. You can also track different types of vehicles, for instance, trucks, maybe if you see more trucks than you normally would, or also potentially there's a section of road that maybe large trucks aren't allowed to be driving on. You can flag this type of behavior right away and respond to it in the best way possible. So this is just kind of a little bit of a teaser to show you some of the things coming that we have in our partnership with Nvidia. And I wanted to point out this is really just the beginning. We've kind of showed a little demo that shows counting cars, But once you have this real-time data, I mean, you can bring the entire suite of Esri analysis tools and sort of unleash it on this data. We have, dozens and dozens of tools that you can use to really understand these patterns and behaviors that you're finding in this data. And this data was just never accessible before. It would have been impossible to create this quantity of data and this rich of data without real-time video analytics. So that's all for that we have today to show you. I hope you enjoyed this talk, and feel free to reach out for any questions that you might have.